Hey, Patrick Sullivan here, and I know a few of you were asking yesterday about how does the ideas that we discussed in elementary mathematics move up the food chain into other content areas. And one of the questions posed by one of the attendees was, how does this fit with scientific notation? So let's roll. So let's say we have the number 360,000. And again, as we talked about yesterday, we operate in the decimal number system. So each of those numerals that we've written corresponds with a place value or a size of unit, starting with 10 to the 0, and we move up. And so again, doing a little cheat here, but 360,000, we say that is 360 times 10 to the third. So again, we're going to use the idea. Again, numbers are a tethering of quantities and sizes of units. And so we're going to use the principle we talked about of equal exchanges again to get this. We're not going to talk about moving decimals. We're going to talk about equal exchanges because we want to develop flexibility with numbers. So 360 is also, if we decrease the quantity by a factor of 10 and increase the size of the unit by a factor of 10, we get 36 of a unit of 10,000, which is 10 to the fourth. Or going one step further, 3.6 of a unit of 100,000. So in this case, all three of those numerical expressions are equal to each other, and they are equal exchanges, and we describe that in terms of decreasing by a factor of 10 and increasing by a factor of 10. So let's look at another problem. Let's put a bunch of zeros in 365. And now I'm going to do as I did before. This time I have tenths, I have hundredths, I have thousandths, I have 10,000ths, 100,000ths, millions, and 10 millions. Now, I could shortchange this, and I'll talk about this in a minute, but I'm going to go with the same idea as before. I have 365 10 millions. So I'm going to start with my 365. That is, once again, that's going to be my quantity. And my size of unit is 10 millions. There's my quantity, and there's my size of unit. And I'm going to use the same idea as before, but this time I'm going to decrease my quantity, as I did last time, excuse me, decrease by a factor of 10. I'm going to increase my size of unit by a factor of 10. I'm going to perform a couple equal exchanges here, as I did before. So I have 36.5 millions and 3.65 hundred thousandths. And there I am. And once again, scientific notation, the size of unit has to be a power of 10, and the quantity has to be between 1 and 10. That's the part of the principles for scientific notation. So I've converted both of those numbers into what we call scientific notation. But again, it's the same principles as we talked about earlier with what we're learning in elementary mathematics, but we're kicking it up a notch to talk about scientific notation. Let's do one more example. 2.8 times 10 to the fifth again. This time we're taking something that's written in scientific notation and we're converting it to standard notation. So again, same idea before. This time we're going to multiply. We're going to increase the size of the unit by a factor of 10. I'm going to decrease the size of the unit by a factor of 10. And we're going to create a bunch of equal exchanges till we get where we want to go, which we want that size of unit to be in terms of ones. And there we go. And again, just a brief overview of tying together some ideas from yesterday. We have the quantity, we have the size of unit. The quantity is increasing by a factor of 10, so we're creating equal exchanges because the size of unit is decreasing by a factor of 10. So there we go. Just a brief little introduction to fitting together the two of the superpower understandings, equal exchanges and numbers as a tethering of quantities and size of units. And you got a little bit of taste of my dog barking.